Okay. Good evening. We are simply repeating the third that was done last day, and also the continue to the fourth one. So what we have so far done is the how to construct an electrochemical cell, and at the anode the oxidation takes place, the cathode reduction state takes place, the cell notation, and ideally polarized electrode. What is it meant by? And it is a substitute for the indicator electrodes that we use in uh, mercury and platinum, like that, which are used in for finding out the potentiometric titrations. Ideally polarized electrode, an electrode at which there is no transfer of across the electrode electrolyte interface. Overall potential ranges is called an ideally polarized electrode. Only the potential is measured here. There is no electron transfer reactions. Behavior of an ideally polarized electrode is no charge transfer possible at an ideally polarized electrode. The behavior of such an interface when the potential across the electrode is changed resembles that of a plain capacitor. An ideally polarized electrode follows a standard capacitor equation. Capacitor equation is the capacitance into the potential. That is called the charge that is contained in a capacitor. Q is equal to C into E. Q is the charge stored in the capacitor in coulombs. CD is the capacitance of the in farads, and E is the potential of the across the capacitor. When voltage is applied across an ideally polarized electrode, the electrical double layer is charged until equation 6. This is the equation 6 is obeyed. During charging, a charging current flows through the system. That is what we are measuring in the potentiometer titrations using platinum indicator electrode, or in polarography, dropping mercury electrode and other things. So significance of charging current is contributes to the total current measured, cannot be ignored, especially for low Faraday currents, may exceed Faraday currents in such cases. To better understand the effect of charging, we need to examine mathematically the responses of an ideally polarized electrode to various electrochemical stimuli. Now, an ideally polarized electrode can be in an equivalent circuit is a capacitance and a resistance in series. The ideally polarized system can be represented as a capacitance in series with a electrolyte resistance. The potential step is applied in, that is, the potential is raised from an initial value to a higher value and held at a higher value. Okay, this is what is called. So result of a potential step application is the double layer is charged. We are going to see what is double layer, and I think in little later, maybe in another one or two presentations. Q, the charge that is stored in a capacitor, is called the capacitance into the voltage. This is the equation 6. The applied voltage must be equal to the sum of the voltage drops across the resistor and capacitor. This was a question asked. Suppose if I were to measure with a potentiometer or a voltmeter the potential drop across the capacitor and across the resistor, that is what is called the behavior of such an interface when the potential across the drop across the electrode is changed resembles that of a plain capacitor. An ideally polarized electrode follows the standard capacitor equation. We have already done that. When voltage is applied across an ideally polarized coil, the electrical double layer is charged until equation 6 is obeyed. During charge, a charging current flows. The charging current contributes to the total current. It can be cannot be ignored. Okay, especially for low Faraday currents, may exceed Faraday currents in such cases. To better understand the effect of charging, we need to examine mathematically the response of an ideally polarized electrode to various electrochemical states. The ideally polarized electrode is a capacitor and a resistance in series. A potential step is applied. The potential is raised from an initial value to a higher value and held at that higher value. This the double layer is charged accordingly. Q, the charge that is accumulated in the double layer, is capacitance into the applied voltage must be equal to the sum of the voltage drops across the resistor and the capacitor. That is, if I were to measure the potential drop here and the potential drop here, then that is called the applied voltage must be equal to the sum. Okay, the applied voltage is, we are applying the voltage across this and this. So suppose if I were to say, let us assume that I apply 1 volt here, zero point 0.4 volt is dropped here and 0.6 volt is dropped here. The all depends upon the capacitance and the resistance value. It may not be 0.4 and 0.6, but it is only an example. So E, the total voltage is equal to ER, the resistance drop across the resistance and the drop across the capacitor. Applying Ohm's law, the E resistance is equal to IR drop. Okay, I is the current, R is the resistor of the resistance of the resistor. From equation 6, E, the potential across the capacitor is Q by CD, because Q is equal to CD into E. So E is the potential drop across the capacitor is the charge accumulated by the capacitance. Therefore, the potential, total potential is the IR drop, the drop across the resistor and the drop across the capacitor. This is the question that was asked last time. I did not answer that because I did not want to confuse you at that time. Whenever there is a potential that is applied and as a number of components are in series, the total potential is dropped across the components in the series. Please remember that. By definition, current is the rate of flow of charge. Therefore, I will be equal to 2 dq by dt. So equation 10, okay, this potential can be written as dq by dt. I is the dq by dt. So dq by dt is q minus q by r rcd in plus ce by r. Okay. So ideal solution, ideal condition for a thing is that a capacitor is initially uncharged. That is, q is equal to 0 at t is equal to 0. So the charging of the capacitor will be given by q is equal to E into CD into 1 minus e to the power of t time Rs resistance, CD the capacitance. 13. So differentiating equation 13 with respect to time, we get the current. Okay, the current is given by E by Rs into e to the power of t into Rs into CD. Equation 14 describes the time dependence of the charging current in response to a potential step. Okay, potential step means what is what our potential we are applying. Okay, from 0 volt to 5 volt or like that. The product of Rs and CD has units of time called the time constant. Okay, the product of resistance into the capacitance as that is why it is tau. Okay, for typical values of Rs and CD, the charging current dies down to an insignificant level in a few hundred of microseconds. We will come to all these things in an electronic circuits. Any Faraday current must be measured after this time period to avoid the influence of the charging current. So this is, if I were to do an electrochemical reaction, which is going to give rise to a Faraday current, the Faraday current must be measured under the without the influence of the charging current. The charging current will be taking place, but it will be only some microseconds. Investigation of electrochemical behavior involves holding certain variables constant while observing the trends in others. Okay, this is another thing that we have to understand. In electrochemistry, the variables are very limited: potential, current, and maybe concentration and time. So the typical variables are shown here. So that there are two electrodes. In the electrode, the potential, current, and the quantity of electricity Q, E, I, and Q are measured. The external variables are temperature, pressure, and time. The electrode variables are the nature of the material, the surface area of the electrode, the geometry, the surface condition. Then if it is a flowing cell or something like that, the diffusion and conversion. Even if it is a static cell, the diffusion and conversion to the electrode, surface concentration, adsorption. Now if I were to take the electrode, the solution variables are bulk concentration of the electroactive species, C0 the oxidizing species, C reducing species, concentration of other species, electrolyte, supporting electrolyte, pH, and other things. We will understand all supporting electrolyte and other things little later. Because we want to carry out an electrochemical reaction, the cell should not be highly resistive. So therefore, we will add a supporting electrode which will not undergo electrochemical reactions under the potentials that we are applying. Only the depolarizer, the electroactive substance alone will undergo, but the current will be flown by the depolarizer and also the supporting electrolyte. Okay, that is why the supporting electrolyte is used. The solvent, okay, you normally solvent is aqueous solvents, but in most of the electrochemical measurements, but it is, can be also other solvents also possible. From the fuel cell point of view, the main aspects of interest are electrochemical kinetics, that is the oxidation reaction and reduction reaction. For ionic and electronic resistance in electrolyte and electrodes, mass transport through the electrodes. These processes are illustrated in the following schematic thing. So you can see the electron flow or electron acceptance, that is what is called the electron flow is reduction, electron acceptance is oxidation, electron transfer we will see later in addition later on. So when we transfer an electron from a reduced species to an oxidized species, or from an oxidized species to a reduced species, then the transport of the species from this bulk of the solution and mass transport or diffusion. So the current may be written as the rate of change of charge, I is equal to dq by dt. The number of moles participating in an electron electrochemical reaction is given by n, number of moles. N is number of moles, small n is the number of electrons. Please remember that. So capital N, number of moles that are converted, is Q, the total charge that is flowing, divided by number of electrons transferred per species into the Faraday. Faraday is an equivalent, therefore number of electrons has to be put there. The electrochemical reaction rate can be written as rate is equal to moles per second, so dN by dt. Rate in converting this, dN is the number of moles, dN by dt is simply the rate. Now converting it into electrochemical units, rate will be equal to 1 by NF into dq by dt. Okay. So therefore, there thus the current is a direct measure of the rate of the electrochemical reaction. Sometimes it is convenient to express quantities as fluxes, dividing the rate by the active area of the electrode. Then we get the flux at the electrode. Therefore, I is the current divided by NF into A. Okay, we will come to it. This is called current density. We will come to it later. Replacing I by A by small I, current density amperes per square centimeter, we get flux will be equal to I by the current, I by NF into A. Okay, that is equal to I itself. I by A is small I, so small I divided by NF. Now, Faraday reactions have an equilibrium potential based upon the reaction free energy. Okay, we know very well delta E n minus NFE is equal to delta G is. So on passing Faraday current, the potential shifts from this equilibrium potential. This shift is termed as the polarization. Extent of shift measured by over potential, where equilibrium applied potential minus equilibrium potential is the over potential. We will see very clearly what is over potential later on when we are dealing with some of the devices. So polarization and over voltage. Before that, we will simply understand that, and then we will see all the Faraday reactions have an equilibrium potential based upon reaction free energy. Therefore, over potential is E, the applied potential, minus E, equilibrium potential. Information about the Faraday reaction is gained by determining the current as a function of potential or vice versa, or measuring at a constant current what is the potential. The resulting curves, okay, we will see later on, are called polarization curves or VI. I already told you in electrochemistry, potential E is the potential, E versus I or V versus I. V is the volt supplied. Obtaining such curves is critical part of fuel cell research and also all other experiments. So if you look at the V versus I curve, it is the solid line. Okay, we will not worry about the dotted line. We will see later on. So what we are seeing is there is a drop of the voltage on the current at the initial range, which is called maximum theoretical voltage is 1.23, but even at a very small current, less than a milliampere or milliamperes, around 250 milliamperes, it voltage becomes 0.9. Then up to 1.5, 1.6 volt amperes, the voltage drops to 0.6. Then after that, it is steeply falling down. So this region is called the mass transport losses. The nearly linear portion. Okay, nearly, it is not linear, but it is nearly linear portion. This is called ohmic losses because IR drop. Here the maximum loss is there. It is called the activation loss. We will understand all these things later. Activation loss, what is the parameters on which activation loss is present, ohmic loss is present, and mass transport loss is there. Normally we will not operate at such high currents. Therefore we will avoid using the mass transport losses. Only ohmic loss and activation loss will be the predominant in the polarization curves. Okay, the same curve is shown. So the region of activation polarization is the steep drop in the first few milliamperes of the current rod, then the slow drop, which is called the ohmic loss, then the steep loss is called the mass transport loss. The resistance are the electronic resistance due to electronic current through the electrodes and the external circuit can be minimized by using electron conducting materials. So therefore, the electronic resistance of the semiconductor or the electrodes can be minimized by using the conducting materials at the electrode. Ionic resistance is due to the electrolyte, due to the ionic current through the electrolyte, needs to be considered seriously as it leads to losses. That is why we said we will add a supporting electrolyte, so that the IR drop in the solution will be very small. At the anode, excess positive ions build up positive charge. At the cathode, excess of negative ions build up negative charge. Build up ionic charge released by the ion transport. Positive ions move from anode to cathode and vice versa. Okay, positive ions move from anode to the cathode. Negative ions move from the cathode to the anode. The fraction of the current carried by the positive and negative ions is given by T plus and T minus. So that is what is called the transport number. Now that the sum of this transport number must be equal to 1. Now there can be many T plus, many T minus, but all of them put together, the sum of T plus, sum of all T plus and sum of all T minus must be equal to 1. So now we'll look at the resistance in electrochemical cell. We already seen electronic resistance and ionic resistance. At the anode, excessive positive ions build up positive charge. At the cathode, excess negative ions build up negative charge. So this is what we have done. Okay, so this is what I have showed, that is sigma Ti is equal to 1. This equation is valid when more than one type of ion is in solution is present. The transport numbers of ions determined by the conductance of the electrolyte. We will see later on how to determine the transport number of that. The conductance of an electrolyte, even though we have not told that we will not be dealing with the conductance, but it is necessary for us to understand what is conductance. So the conductance of a solution is the area of the electrode, active area of the of contact, length, this length, okay, the small l is the length, thickness of the electrolyte matrix. Kappa is the conductivity, intrinsic property of the electrolyte, whereas L is the conductance. Conductance has units of Siemens and conductivity as Siemens per centimeter. The conductivity of an electrolyte has a contribution from every ion in solution. Conductivity is proportional to the concentration of the ion C, charge on the ion Z, a property that determines its migration velocity called the mobility. Okay, these are all very intricate things. That is why we are spending that time here. Mobility is defined as the limiting velocity of an ion in an electric field of unit field strength. Okay, for example, if you take me, I can have a mobility for so many miles per hour or so many miles per second or something like that. Whereas here, the mobility of the ions, okay, is the limiting velocity of the ion under the influence of the electrical field, unit strength of the electrical field. Now, force exerted by an electric field of strength E is given by the force exerted on the ion by an electric field E is given by E in C is the electronic charge, E is the potential, that is the electric field that is applied, into Z, the charge on the ion, where E is the electronic charge. An opposing force exists due to frictional drag. This is represented by the Stokes equation. For example, if I were to move an ion from one electrode to another, the solvents and other things will drag the ions in the opposite direction. That force opposite is given by 6 pi mu into r into v. V is velocity of the ion, r is the radius of the ion, and v is the velocity of the ion in solution. Nu is the viscosity of the solution. This is also can be called as viscous drag. Terminal velocity of ion, when the forces exactly counterbalance each other, the ion attains a steady state velocity called the terminal velocity. This terminal velocity is termed the mobility. Okay, the resistance or the inherent laziness for the ion to move in direction is compensated by the applied potential. So the terminal velocity is the difference of these two. The terminal velocity is termed the mobility when the electric field strength is unity. Mobility itself is when the electric field strength is unity. So mobility mu is given by Z, the charge, E electronic charge. Z is the number of charges on an ion, E is the electronic charge, 6 pi into V velocity into R. R is the ionic radius. So with the above expression for mobility, we write the following expression for kappa. Kappa is the conductivity. If I were to do that, is Faraday into sigma Zi Ui Ci. Now recall transport number T, contribution made by each individual ion to the total current in the solution. So expression from transport number also can be now written by in terms of the molecular parameters or the ionic parameters, Zi Ui Ci divided by the sum of all the ions. Therefore, that is what is called the transport number of that ion. The transport number may be represented as the ratio of the contribution to the conductivity made by that particular ion to the total conductivity of the solution. Okay. Resistance is defined as R is equal to 1 over kappa into A. A is the area. The ionic resistance is inherent property of an ion in motion and the electrolyte. Effective resistance in electrochemical cells, Ohm's law, V is equal to IR drop. Okay, potential is IR. R is will introduce a potential drop V, which will increase with current. More approximately, Ohm's law is expressed by I is equal to, we can now we express the more Ohm's law. I will be equal to kappa into d phi by dx, where d phi is the potential gradient. Okay, we were already told that it should be under a potential gradient or field strength. So now minimizing the R and IR compensation. R can be minimized by minimizing distance between the electrodes. Okay, R, the resistance. Increasing area of contact, not preferred, that is governed by many other factors. Need to realize some portion of the R will always be remain. So realistically, E measured, the potential measured is E cathode minus E anode minus the IR drop. Within this, suppose if I were to take an electrochemical cell, a cell like this, then it is depends upon the two electrodes and the electrolyte in between them. So that is what is the E measured. Okay, E cathode and E anode are the single electrode potentials, but for a cell, E measured will be equal to E cathode minus E anode minus IR drop. If the value of R is known, one can compensate for ohmic drop. The compensated E is a closer representation of the actual E. E compensated or actual E will be equal to E measured plus IR drop. Okay, so therefore the measured value plus the IR drop is the compensated potential of the cell. I will stop at this point and answers any questions you have. You can ask any questions you want. Yes, please ask the question now. Repeat the question. Please repeat the question. I'm not hearing you. You have muted your system. You Sanjeev Gupta, Sanjeev, you are not. You are talking, but I am not hearing you. You have muted your. Hurry, tell Sanjeev to speak in the microphone. Okay, type it.
Actually, my system is not working.
Okay. I am not hearing at all. Okay, you can type if you want. Okay, if you don't have questions, you can send the mail. We will answer that question next week, next presentation, which is on Saturday. Okay.
Thank you, sir.